This ground lesson covers weight and balance for the Cessna 150M. While it is assumed the viewer has a working knowledge of basic aircraft loading theory, some review of important concepts is included. The pilot's operating handbook will be referenced throughout this presentation. Let's begin by reviewing the weight limitations of the aircraft. The Cessna 150 has a maximum gross takeoff and landing weight of 1,600 pounds. There is a large baggage area located behind the seats that is divided into two sections. The forward section is referred to as Baggage Area 1 and extends from the back of the seats aft to the tie-down rings. Baggage Area 2 is aft of and adjacent to Baggage Area 1. The midpoint of Baggage Area 1 is 64 inches aft of the datum. The center of Baggage Area 2 is 84 inches aft. The datum line from which all distances are measured is the firewall on the Cessna 150. The maximum weight in Baggage Area 1 is 120 pounds. The limit for Baggage Area 2 is 40 pounds. However, the total combined weight of both baggage areas cannot exceed 120 pounds. The useful load is found by deducting the aircraft empty weight from the maximum gross takeoff weight. The useful load is the total amount of fuel, baggage, and passengers that can be carried within the limitations specified by the manufacturer. Recall that the empty weight includes all installed equipment, full oil and hydraulic fluid, and unusable fuel. In this example, we used a typical empty weight of 1,150 pounds to compute a generic useful load of 450 pounds. However, it is important to always use the current empty weight applicable to your specific aircraft by referencing the pilot's operating handbook. The term payload refers to the maximum weight of passengers and baggage that can be carried with a specified amount of fuel. To determine the full fuel payload, deduct the maximum usable fuel from the useful load. In our example, this yields a maximum payload of 315 pounds. Of course, the payload can be increased by reducing the amount of fuel, but doing so will decrease the range. Again, refer to the POH for your airplane for the actual empty weight when performing any weight and balance computations. The aft center of gravity limit is 37.5 inches after the datum across the entire operating weight range for the aircraft. The forward CG limit is a function of the weight of the airplane, beginning at 31.5 inches after the datum for weights at or below 1,280 pounds, then tapering aft to 32.9 inches at the maximum gross weight of 1,600 pounds. Recall that there are three longitudinal or pitch forces acting on the aircraft in flight. The center of gravity is the point through which all weight acts, and is controlled by the way in which the pilot arranges a load in the aircraft. The center of lift represents the sum total of the collective lift forces. The relationship of the center of gravity to the center of lift is an important one that affects the aircraft's stability and other characteristics. With the center of gravity ahead of the center of lift, the aircraft experiences a nose-down pitching moment. This is offset, however, by the tail-down force of the horizontal stabilizer and elevator. As the CG moves forward, a larger tail-down force is required to offset the greater nose-down tendency. Whether the pilot chooses to hold more nose-up elevator pressure or trims the aircraft, the result is the same. More downward lift from the tail is generated, which is equivalent to hanging a weight from the tail, making the aircraft heavier. With an aft CG, the opposite occurs. As the distance between the center of gravity and the center of lift narrows, there is less of a nose-down pitching force, and therefore less tail-down force is required. This reduces the aerodynamic weight of the airplane. With a forward CG, the pilot can expect a heavier aircraft, which increases stall speed and decreases performance. However, with the greater distance between the center of gravity and the center of lift, pitch stability improves with a forward CG. While an aft CG will decrease stall speed and improve performance, stability will decrease and stall and spin recovery will not be as easy as with a forward center of gravity. Despite these characteristics, it should be remembered that as long as the CG remains within limits, the aircraft will exhibit adequate pitch stability and controllability. Let's now take a look at a sample loading problem to help you become familiar with the process. The basic empty weight and moment must be obtained from the aircraft's approved flight manual or POH. The current weight and balance information is located in the front pocket of the POH supplements binder in the flight dispatch kit. For this flight, we'll use a pilot weight of 180 pounds. The fuel quantity was checked using the dipstick and found to be at 20 gallons total. Baggage area 1 is loaded with 50 pounds of luggage, and baggage area 2 with 20 pounds. TimeBuildUSA has created a loading form to assist pilots in their weight and balance computations. These forms are available in the company binder in the flight dispatch kit. Here we've entered the weights onto the form and totaled them up to arrive at a gross takeoff weight of 1,508 pounds, which is comfortably under the limit of 1,600 pounds. One thing to pay careful attention to is that the moment values in the form are divided by 1,000. Be certain to divide the starting basic empty weight moment by 1,000 as we have done here. The rest of the moments will be obtained from the loading graph found in the POH. Let's start with the fuel. The loading graph contains 4 lines extending from the origin in the lower left. In the upper part of the graph, you'll find a legend that matches a line style to a particular station. To use the chart, enter from the left side with the known weight and move right until intersecting the applicable line. Then move straight down from there to find the moment, which has already been reduced by 1,000. In our example, the plane is loaded with 20 gallons of fuel, which is 120 pounds. Starting on the vertical axis at 120 pounds, move right until reaching the small dashed line representing the fuel tank station. Reading straight down from there gives a moment divided by 1,000 of 5.1. Note that each vertical line on the graph represents a moment divided by 1,000 of 2/10. Add the moment divided by 1,000 of 5.1 on the respective line of the form for the fuel. Next, we'll find the moment for the pilot who weighs 180 pounds. Enter the graph on the left side at 180 pounds and move right until reaching the solid line representing the pilot and front passenger station. From there, move straight down to obtain a moment divided by 1,000 of 7.0. Enter the moment on the line adjacent to the pilot on the form. Next, return back to the loading graph to obtain the loaded moment for the baggage area 1 that contains 50 pounds. Using 50 pounds and a large dashed line on the loading graph representing the baggage area 1, we get a loaded moment divided by 1,000 of 3.2. Transfer the moment onto the form as we've done before for baggage area 1. Lastly, determine the loaded moment for baggage area 2, which contains 20 pounds of luggage, and transfer onto the form. Finally, total all of the moments on the loading worksheet. Using the total weight and moment divided by 1,000, plot the intersection of both values on the CG moment envelope in the POH. If the CG falls within the boxed area, then the aircraft is properly loaded. Note that the CG becomes more forward as you move left on the graph. An alternative way to check the loading is to compute the center of gravity and use the CG limit chart in the POH. To compute the CG, multiply the total moments by 1,000 and divide the result by the weight. The CG location is found to be 35.7 inches after the datum. Plotting the intersection of the CG and weight on the chart shows the CG to be within limits. Because the arm of the fuel tanks is very close to the CG range of the aircraft, the consumption of fuel will not materially affect the center of gravity during flight. It should be noted that as fuel is burned, however, the CG will move very slightly forward. To prove this, let's compute the landing CG after a 2-hour flight in which 12 gallons of fuel was consumed. The computed landing CG is determined to be 35.5 inches after the datum, which is only 2/10 of an inch forward of the takeoff location. This concludes the weight and balance presentation for the Cessna 150M. This has been a presentation of TimeBuildUSA. TimeBuildUSA offers exceptionally clean late model Cessna 150 aircraft to pilots for extended rental periods. Now you can have access to your own aircraft for days or weeks at a time. Visit us online at TimeBuildUSA.com.